Dear learners, in this session we will be discussing about group 15 of periodic table. After this discussion, you will be able to differentiate properties of group 15 elements, relate the exceptional behavior of first element of group with its size and absence of d orbital, describe general trends in chemistry of group 15 elements, explain the method of preparation of nitrogen, discuss properties of nitrogen, appreciate uses of nitrogen. You are familiar with the design of periodic table. P block is on extreme right of periodic table and comprises group 13 to group 18. The elements in which last electron is filled into p orbital are called p block elements. Since p orbitals can accommodate 6 electrons, accordingly elements from group 13 to 18 are considered as p block elements in the periodic table. The valence shell electronic configuration is Ns2 Np1 to 6 except for helium which has 1s2 configuration. First member of each group of p block element differs from remaining members of their corresponding group due to their very small size, high ionization enthalpy and absence of d orbitals. We will discuss this anomalous behavior at relevant places. Today, we will discuss about group 15 elements which is called nitrogen family. The elements present in this group are nitrogen N, phosphorus P, arsenic As, antimony Sb, bismuth Bi and moscovium Mc. This is interesting to know that moscovium, which is represented by a symbol Mc having atomic number 115 and atomic mass 289. This is a synthetic radioactive element and is available in very little amount with a very short half life. So, its chemistry is yet to be established. Therefore, in today's discussion, our focus will be on first 5 elements of the periodic table and not on moscovium. We know that molecular nitrogen comprises 78% by volume of the atmosphere. In the earth crust, it occurs as child saltpeter, that is sodium nitrate, and Indian saltpeter, that is potassium nitrate. Nitrogen is also present in plants and animals as a component of proteins. Phosphorus occurs in minerals of the apatite family, which are the main components of phosphate rocks. Phosphorus is an essential constituent of animal and plant matter. It is present in bones as well as in living cells. Phosphoproteins are present in milk and eggs. Arsenic, antimony and bismuth are found mainly as sulfide minerals. My dear learners, all the members of this family tend to follow a general trend in properties. Let us discuss them one by one. As you can see, covalent radius increases down the group, but only a small increase is observed from arsenic to bismuth. This is due to the presence of completely filled d and or f orbitals in heavier members. There is a decrease in the ionization enthalpy down the group. Ionization enthalpy is the amount of energy required to remove valence electron. As atomic size increases down the group, effective nuclear charge decreases, so ionization enthalpy also decreases. Metallic character increases down the group. This is due to decrease in ionization enthalpy and increase in atomic size. Nitrogen and phosphorus are known metals, arsenic and antimony are metalloids and bismuth is a metal. Because of the extra stable half filled electronic configuration and smaller size, the ionization enthalpy of group 15 elements is much greater than that of group 14 elements in the corresponding periods. Electronegativity also decreases down the group. However, amongst the heavier elements, the difference is not that much pronounced. All the elements of this group are polyatomic. Dinitrogen is a diatomic gas, while all other are solid. Boiling point and density increases down the group, but the melting point increases up to arsenic and then decreases up to bismuth. Now, let us discuss about oxidation states and trends in chemical reactivity. The common oxidation states of these elements are -3, +3 and +5. The tendency to exhibit -3 oxidation state decreases down the group due to increase in size and metallic character. The stability of +5 oxidation state decreases and that of +3 oxidation state increases down the group. This is due to inert pair effect. This is the reason that bismuth 5 is a good oxidizing agent. Nitrogen exhibits +1, +2, +4 oxidation states also when it reacts with oxygen. Phosphorus also shows +1 and +4 oxidation states in some oxo acids. In the case of nitrogen, all oxidation states from +1 to +4 tend to disproportionate in acidic solution. For example, nitrous acid on heating disproportionate into nitric acid and nitrogen monoxide. Similarly, in case of phosphorus, nearly all intermediate oxidation states disproportionate into +5 and -3 both in alkali and acid. Anomalous behavior of nitrogen, first member of p block element, differs from remaining members of their corresponding group. So, nitrogen shows anomalous behavior due to its small size, high electronegativity, high ionization enthalpy and non-availability of d orbitals. Nitrogen has unique ability to form p-pi multiple bonds with itself and with other elements having smaller size and high electronegativity such as carbon and oxygen. Heavier elements do not form p-pi bonds as their atomic orbitals are so large and diffused that they cannot have effective overlapping. Thus, nitrogen exists as diatomic molecule with a triple bond between the two atoms. On the contrary, phosphorus, arsenic and antimony form single bonds, as while bismuth form metallic bonds in elemental state. However, the single N-N bond is weaker than single P-P bond because of high interelectronic repulsion of the non-bonding electrons owing to small bond length. As a result, the catenation tendency is weaker in nitrogen. Another factor which affects chemistry of nitrogen is the absence of d orbitals in its valence shell. Besides restricting its covalence to 4, nitrogen cannot form d-pi p-pi bond as the other heavy elements can. Let us understand how group 15 elements react with hydrogen. All members form hydrides with formula EH3, where E can be nitrogen, phosphorus, arsenic, antimony or bismuth, and they are in the oxidation state -3. The hydrides show regular gradation in their properties. Central atom has sp3 hybridization, but geometry is distorted due to the presence of lone pair. The presence of one lone pair on central atom make them Lewis base, and basic strength decreases down the group among hydrides, that is ammonia being most basic, followed by phosphine, then arsenic H3, antimony hydride, and last bismuth hydride. Due to high electronegativity and small size of nitrogen, ammonia exhibits hydrogen bonding in solid as well as liquid state. As a result, it has higher melting and boiling points than that of phosphine. There is decrease in bond dissociation energy down the group. Bond become longer and weaker. This decreases the stability of hydrides down the group and they can provide hydrogen easily. That is why their reducing character increases. Now, you can easily understand the reason for bismuth hydride being strongest reducing agent. Let us understand how group 15 elements react with oxygen. All the elements form two types of oxides, E2O3 and E2O5. The oxide in the higher oxidation state of the element is more acidic and their acidic character decreases down the group. The oxides of the type E2O3 of nitrogen and phosphorus are purely acidic, while that of arsenic and antimony are amphoteric and those of bismuth is predominantly basic. But nitrogen shows anomalous behavior. It forms oxides ranging from oxidation state +1 to +5. Let us understand how group 15 elements react with halogens. These elements react with halogens to form two series of halides, which are trihalides, that is EX3, and pentahalides, that is EX5. Though nitrogen exhibit +5 oxidation state, but it does not form pentahalide like NF5, while PF5 exists. Have you ever thought why? It is because nitrogen does not have d orbital in its valence shell. Pentahalides are more covalent than trihalides. This is due to the fact that in pentahalides, oxidation state of central atom is +5, while in trihalides, the oxidation state of central atom is +3. Since elements in +5 oxidation state will have more polarizing power than in +3 oxidation state. This increases the covalent character of bonds in pentahalides. All the trihalides of these elements except those of nitrogen are stable. In case of nitrogen, only NF3 is known to be stable. Trihalides except bismuth fluoride are predominantly covalent in nature. Now, let us discuss about the first element of group 15, that is dinitrogen. Dinitrogen is a colorless, odorless, tasteless and non-toxic gas. Nitrogen atom has two stable isotope, nitrogen 14 and nitrogen 15. Commercially, nitrogen can be prepared by liquefaction and fractional distillation of air. Liquid dinitrogen distills out first, leaving behind liquid oxygen. In laboratory, it can be prepared by the thermal decomposition of ammonium dichromate, treating an aqueous solution of ammonium chloride with sodium nitrite, and the thermal decomposition of sodium or barium azide. If we discuss about its chemical properties, it is inert at room temperature because of a strong N-N triple bond. However, at higher temperatures, it directly combines with some metals to form predominantly ionic nitrides with non-metals to form covalent nitrides, with hydrogen to form ammonia and with dioxygen to form nitric oxide. In next session, we will discuss some important compounds of nitrogen. To summarize today's discussion, we conclude that group 13 to 18 of periodic table consist of p block elements with their valence shell electronic configuration NS2 NP1 to 6. Group 15 is nitrogen family with configuration NS2 NP3. Their high ionization enthalpy is attributed to stable configuration. Nitrogen is most abundant in air but inert at room temperature due to high bond enthalpy of NN triple bond. It also shows anomalous behavior. This is due to very small size, high charge density, high ionization enthalpy and absence of d orbitals. It has only 4 valence orbitals, so it cannot expand its frequency beyond 4 and cannot form compounds like nitrogen pentafluoride, but it can form compounds with oxidation state plus 5 because it has 5 valence electrons to be shifted to more electronegative oxygen atom. The common oxidation states are plus 3 and plus 5, but nitrogen forms oxides with all the oxidation states from 1 to 5. Group 15 elements form hydrides, oxides as well as halides. Before we end today's discussion, let me leave you with some assignment questions. Question 1. Why bismuth 3 is more stable than bismuth 5? Question number 2. Why thermal stability of hydrides decreases down the group? Number 3. Explain given trend of basic strength of group 15 hydrides, that is ammonia being most basic followed by phosphine, then arsenic hydride, antimony hydride and bismuth hydride. I hope you have understood the concepts discussed. We will discuss remaining part of nitrogen family in next session, but till then take care.